Mhm. It's being recorded. Yeah.
I think Steve, yes, Steve is the organizer.
I see.
So he would, but this is a different level.
No, it's okay. Yeah.
Yes, yes.
Yeah.
Madison, who came to the talk, come to the scene, thank you for coming summertime.
Oh yeah. Thanks.
We'll talk about realization information, the local constants, so all this range this work. The stage is yours.
Sure. Thanks. Yeah. Thanks, Das. Thanks for having me here. So today I'll be talking about I think two basic and fundamental questions in statistics, mean and location estimation. And the talk is based on joint works with Paul Valiant, Shubham Gupta, and Eric Price, who I'll acknowledge like throughout the different sections of the talk. So before I dive into the specifics of mean and location estimation, I just want to maybe motivate a little bit this line of research that I'm trying to pursue here. And as with most theory talks, the overarching theme is just that theory does not align with practice. Like the available theory in statistics, and in fact other areas as well, doesn't necessarily capture what we want to be doing in practice. So this is very abstract. What do I mean by this? So in my mind, there are really two different main sets of issues as preventing theory from being applied in practice. The first set of issues is much more frequently discussed and has more to do with problem formulations. For example, what kind of a data access model do we have? What are we allowed to do with the data? So as slightly more concrete examples, a lot of classical statistics assumes that we get i.i.d. samples from some underlying distribution, and we want to do inference on the underlying distribution. But the world isn't always i.i.d. We might have Markovian data, we might have graphical models, we might have even more complicated things. We might have bandits, we might have hidden Markov models and adversarially contaminated data and so on. And also now that we have computers, we care about computational constraints. We care about having efficient algorithms. We might even want low memory streaming algorithms. We might want low communication distributed algorithms and so on and so forth. Lots of cool works, along these lines from the previous few decades. But that's not the set of issues that I'm really focusing on for the purpose of this talk. I think there's a second set of issues that is less frequently discussed, and that has to do with the kind of analysis we want to be doing, or rather the goals that we are setting for our analysis, and ultimately what kind of theorems we want to write down. And this is a set of issues that is prevalent even for the most basic statistical questions. Just a little bit more concretely, when we write down the theorem, are we making very strong technical assumptions like distributional sub-Gaussian assumptions? Are we maybe doing asymptotic statistics? Are we taking limits in the right way? Do these results actually hold in finite number of samples? And then when we claim that an algorithm is optimal, how optimal actually are they? So the second set of issues is what I'm going to be focusing for this talk. This is still a little bit abstract, so I want to really illustrate the point with the concrete question of mean estimation in one dimension. So I guess I go admit, okay. So mean estimation in one dimension, really one of the most basic statistical questions. So we have some unknown distribution D over the reals. We take i.i.d. samples from it, and the goal is to, with high confidence, estimate the mean of the distribution. So one of the most basic questions you could ask. So let's consider what we know about the problem from around, I don't know, 15 or maybe 40 years ago, something like that. So of course, we have the beloved central limit theorem, what it says is that if we fix the distribution, and we take the number of samples to infinity, the sample mean works pretty well. We have the central limit theorem that says that the error distribution is going to look like a Gaussian. And it's not too hard to show that Gaussian behavior is the optimal thing you could be doing. Now, I just told you something is optimal, so why am I giving a talk here, right? Well, on the surface, so what's wrong with this? On the surface, we don't have infinitely many samples. So the question is, in finite samples, when do we get central limit behavior? Now, one cop-out answer for this is if we just assume that the distribution were Gaussian to begin with, then of course, by definition, the sample mean is a Gaussian. A little bit more generally, we might assume sub-Gaussian tails. If the distribution has roughly Gaussian-like tail behavior, then the sample mean also works really well. On the other hand, in the real world, we also have a lot of heavy tail distributions. In particular, even Bernoulli coins, if they're somewhat biased enough, they actually exhibit heavy tail behavior. So then the question becomes, when do we get central limit behavior for heavy tail distributions? And the answer to that is if we only care roughly around the constant probability of failure around the center of the bump, things look roughly like Gaussians, a little bit more technically Chebyshev inequality. But statistics 101, we also know that sample mean is very sensitive to things that are look like outliers. So rare events for heavy tail distributions will tend to unluckily see things that are very far away from the true mean and just completely throws off the estimate. So rare events, low probability events, we might be screwed by. On the other hand, we do care about high confidence estimation in at least certain real life applications. If we are trying to discover laws of physics, or if we try to build a nuclear reactor, we want to be really, really confident. We don't want anything to fail. So this is begging for a finite sample and high probability theory of, even the most basic question of mean estimation in one dimension. Fortunately, around 40 years ago, we do have some answers. We do know things about mean estimation. The very standard, by now standard medium means estimator. Basically, you just take your samples, separate them into groups, take the sample mean of each group and robustify by taking the median. So use the median to ignore outliers, basically. And that has this big old error rate that I'll explain in a bit if you haven't seen this before. The point being that this is basically the Gaussian tail. So this is optimal. Now, again, I've told you that something is optimal. So why am I what am I going to talk about over the next 15 minutes? Well, let's try to see what happens if we run median means on Gaussian data and compare it with the sample mean. So what's going to happen is that we get something like this. So point being that you've got two error distribution curves. The wider, the blue lower, wider bump is the median means. That's a worse error distribution. And the sample mean is, visibly more accurate. And at least for practitioners that I've talked to personally, this one single plot is enough to convince them to not use median means in practice. Just because even on nice Gaussian data, this is visibly at least 30% worse. Yeah. So what went wrong? What went wrong is that we only have bigger optimality. This is only optimal up to constants. So what we really want is to have an algorithm that achieves optimal estimation error, not only up to constants, but with the right constant. And as a sneak peek, the point is that for the estimator I will describe in a bit, we actually get optimal error up to this 1 plus little or 1 term. And if you do run it on Gaussian data, at least in certain regimes, you do recover Gaussian behavior. And the point, of course, is that for heavy tail distributions, our estimator also works better than a sample mean. So it's best of all worlds. That's the point. So that's kind of the motivation for what I'll be talking about over the next 15 minutes or so. The discussion here is really giving a general recipe for talking about basic statistical questions. So first we ask, what are the asymptotic theory guarantees? That theory usually recommends some simple algorithm. We can then ask whether and if the algorithm fails in certain finite sample regimes, how does it fail? And then we can ask, can we maybe recover the asymptotic theory guarantees in finite samples by fixing the failure modes of the simple algorithm? So this is a very general recipe that I want to apply in this talk to 3 very related stories or problems: mean estimation in one dimension. And of course, the next obvious generalization is multivariate high dimensional mean estimation. We have some results on a specific regime of very high dimensionality that I'll specify in a bit. And the last problem is a very related question of location estimation. So location estimation is very close to mean estimation, but here you know the exact shape of the distribution, and all you don't know is the shift of the distribution. So we know the exact shape. And with the extra information, can we do better than mean estimation? And can we, achieve the asymptotic theory guarantees that are, very well studied in classical statistics literature? So these are the 3 problems that I'll be talking about for the rest of the talk. I guess there aren't any questions, so I guess let's dive in. So this is joint work with Paul Valiant. Again, mean estimation, there's unknown distribution D. We want to estimate the mean from i.i.d samples with high confidence. So failure probability, small little delta. The assumptions we make for the underlying distributions is, of course, well, we need to have the mean to exist, otherwise there's nothing to estimate. But furthermore, we're going to assume that the variance also exists, so that central limit theorem even applies, so that there's something to compare against. So this is basically the most minimal assumptions we can make for this question to make sense. The goal then, what is the goal? From the asymptotic theory, according to our recipe, from the asymptotic theory, we know that we want Gaussian behavior, and this is the error rate we want to get. For those of us maybe not too familiar with this expression, let me just explain very quickly. We want the error to scale linearly with the standard deviation, because if we multiply the distribution by a factor of 3, we expect the error to also multiply by a factor of 3. Now, this square root expression is essentially the Gaussian tail. A little bit more concretely is really the Chernoff bound of the Gaussian tail. And the optimal constant is this multiplicative square root 2. And we're going to allow ourselves a little bit of slack of this 1 plus little or 1 term. And ideally, we want this little or 1 term to be decaying at a rate that is independent of the underlying distribution. Because at least qualitatively, if we were to allow the little or 1 to decay with the distribution, then even the sample mean achieves this. So ideally, if we could, we want a distribution independent convergence. Let me very quickly describe prior works before showing you our estimator. Catoni, in very seminal work, showed that if we know the variance precisely or to extremely high accuracy, then it is possible to get this error rate using a very elegant estimator that's actually related to our thing, but I'm not going to go into too much details about Catoni's estimator. And then in his work, and also different work by De Broglie et al., they showed that if the distribution has bounded fourth moment, or really technically bounded normalized fourth moment, you can use that assumption to essentially estimate the variance to very high accuracy and do, use Catoni's estimator, for example, and get the right kind of error rate. And as I mentioned, the classic median means estimator is already big O optimal. And the goal here is to get the best of all these worlds. We want something that has minimal assumptions, no knowledge assumptions, but we get the right constant, right multiplicative constant in the estimation error. So this is a setup, and without further ado, this is our very simple mean estimator. The first thing I want to emphasize is that if you give this as a homework problem to, I don't know, CS100, Intro to Programming, they can do this. They can actually implement this. This is that simple. It's actually usable. So let me, in stages, explain what the algorithm is doing. First step is, well, we need to take inputs. We're going to take the n samples from our distribution, and then we are going to take in also what's the desired failure probability. Now, the actual first step of the algorithm, we're going to compute the median means estimate. And the point here is that this is already big O optimal, as you recall. So this is some rough estimate of the mean that we're going to use 2 steps to refine it into something that is optimally accurate. These 2 steps here, let me explain this slowly. Operationally, in step 3, we have a piecewise linear equation in this variable alpha. The left-hand side is some piecewise increasing piecewise linear function in alpha. Right-hand side is just some constant. We solve for this alpha. And then the last step, just plug it in and evaluate this big expression. Okay, so operationally, this is simple. This is easy to code up. But what are these 2 steps doing? I just threw 2 large equations at you. Well, what is it doing? What are they saying? So to see that, let's introduce some simplifying assumptions just to simplify the thing a little bit to make it easier to interpret. First thing to check is that it's not hard to check that the estimator is shift and scale invariant. So if you add 3 to all your samples, the output estimate also adds 3. Similarly, if you multiply 3 for all your samples, it multiplies by 3. Shift and scale invariance means that we can, without loss of generality, just assume that the underlying distribution has mean 0. The next thing is that, as I was alluding to earlier, these two steps are really refining an initial estimate. So we can take these two steps as a function of the initial estimate, and we can show that it's actually pretty Lipschitz. It's not very sensitive. And given that median means is already pretty accurate anyway, so we might as well assume that the initial estimate is already, let's say, is the true mean, which is by assumption 0, and just see how the estimator behaves from that point onwards. Okay, so with these assumptions, we can now shorten the equations just a little bit to make it a little bit easier to read. And we get these two things. And now we can start to try to interpret what's going on. So to see that, let's look at the very last line and just ignore this 1 minus min stuff here. What remains is just a sample mean by simple notation. And what our estimator is doing then is that for each sample xi, we're going to trim away a little bit of it in some partial weighted sense. For each sample, we trim a little bit away. Now the question is, how do we trim? The how do we trim is governed by this first equation. What this step 3 equation says is that we are going to trim away a total number of 1/3 log 1 over delta many samples in the weighted sense. And how do we apportion the 1/3 log 1 over delta? We're going to measure each sample's distance from the true mean and square it. So square distance from the true mean or the rough mean estimate. And the minus one is saying that we never want to delete more than the entirety of the sample. So it's just a simple threshold. We want to delete everything that we just stop, that we don't give negative samples, basically. Okay, so this is a very simple truncation-based, a delicate truncation-based mean estimator. There's no lower bound. Well, what do you mean by lower bound? I mean, we have explicit rates for everything.
No, delta can be too small, right?
I think it could if it's just huge error, right? Like the little one kind of captures that. I guess maybe e to the minus n would be the reasonable regime. Yeah, reasonable regime. But I think our bounds technically hold even when delta is even smaller, I think. The lower bound, even with like big, huge constants, like in the constant that blows up in that delta. Maybe this is getting into technicality. So like, yeah. Oh, absolute constant. I agree. Yeah, if we want absolute constant, then we need delta to be e to minus n ish. Yeah. But okay, so again, simple truncation based mean estimator. So yeah, reasonable regime is delta is roughly exponentially small, and I guess the weirdest thing about the estimator is perhaps this 1/3 log 1 over delta, like magical number. So this is what I'm going to explain next. Why this magical number? Why is that the right number of samples to delete? So to see why this magical number, we're going to consider the most basic mean estimation problem, just Bernoulli coins. So take n flips of some Bernoulli coin of bias p, and the interesting regime is when p is very biased, p roughly equal to 0. So it's a really rare coin. So the sample mean is just the number of heads. It's a sufficient statistic. If you take the appropriate limits, you might as well just treat the number of heads as some Poisson with parameter n times p. Okay. So recall that we are trying to get sub-Gaussian kind of behavior, Gaussian-like behavior. So on the right here, I'm just plotting the logarithm of the density of the Poisson, of this Poisson with the corresponding Gaussian. I just chose the Poisson parameter to be 100. So as you can see, the annoying issue is that the Poisson has a heavier right tail. So it's easy for us to see too many heads. We get a little bit too many heads, and the goal here is to kind of maybe delete some number of heads before we return the sample mean. So we need this correction. The concrete question then is, what is the right correction? Well, to see what's the right correction, take the delta tail, by which I mean like the shaded area has delta probability for the Gaussian, and do the same for the Poisson, and look at this gap. and this is the gap we basically want to correct. And the point is that if you dive into some, I don't know, several other approximations to the log Poisson PDF, this gap you can actually explicitly calculate. The biggest order term is exactly 1/3 of 1 over delta.
Seems like the drawing is not the shown in the
Oh,
view local.
oh, I see. Oh, that's, yeah, I think there's some issues with the, does this show? Oh, no, even the pointer isn't showing. Oh, that's unfortunate. Yeah, it seems like sharing my laptop screen on Zoom, so I haven't been able to fix it. Still got the idea. Okay. Yeah. So yeah, the gap between the Poisson PDF and the Gaussian PDF, the horizontal gap between delta tail is exactly 1/3 of 1 of delta. So that's kind of how this magical number shows up, even in the most simple case of mean estimation, even for Bernoulli mean estimation, that's how it turns up. And that's why it shows up in our mean estimator as well. So that is pretty much the first part of the talk. We applied the recipe. We started with asking what's the asymptotic guarantees. We understood how the sample mean fails, and then I showed you how to fix the sample mean estimator into something that actually gets, you know, the right error rate up to a 1 plus little 1 with the right constant multiplicative factor. So that's the first part. If there are any questions, it's a good time to pause. On Zoom as well, maybe.
Yeah, if people have questions over Zoom, feel free to type them or just unmute and ask.
I guess not. Okay. So, no. Great. So let's go into this. Oh, sorry.
So one question, I think. One question is what happens if we also allow the several outliers? Because we things to be able to handle them, but
that is what I actually want to discuss with you, actually, for you know, when we talk about research. I believe for now, I haven't actually worked it out. I believe that this estimator should be robust to outliers in some sense of the word. I don't know how to prove it yet. I haven't really started thinking about it, but there doesn't seem to be any reason why it shouldn't be robust. It should be. It should be. It's just simply because we are kind of truncating things that are outlier-ish, and it can't be that bad. But I don't know how to prove it yet. Summer project.
Yeah. And the second question, do you know if there are some natural quantity distributions which have less than 2 moments, which you can say that the optimal quantity distribution? Because kind of things.
Yeah. So this estimator, we could show that there exists some constant that gets. So okay. So there's some other work by maybe Ubek, Lugosi, and Yankee, I think. They did median means can also work in some low moment sense, not the sub-Gaussian rate, obviously, but you can do lower moments. We don't need to write it up. We do have an analysis that at least beats their constants. So we could actually extend the analysis to these lower moments as well. As for what the right constants are, I have no idea. I thought about this. I'm not even sure what the right asymptotic theory is. There are all these like stable distributions and stuff. At least Wikipedia confused me, so I kind of didn't pursue it too much. Yeah, but all I can say is that we have better constants than median means, at least for their analysis. But it's unpublished. It's kind of, we haven't written it up yet. We have some MATLAB plots we know is true, but I haven't, yeah.
First of all, sorry for missing the first part.
Oh, no.
I tried to interpolate what you there.
Yeah.
It's something else to look at. It's better, but it's kind of variable. So my question is, so the following question, first of all, if I mean the lower bound, right? The lower bound is over the class of distributions with finite two moments, right?
Yep.
So and so the lower bound, like this one, is the optimal constant in terms of this lower bound. Right?
For Gaussians, in fact, it's from Gaussians. That's a lower bound. Yeah.
So it's the famous houses.
Yeah. Are you asking beyond worst case kind of question? Like, can we do better?
No, the next question would be like if I would, for example, have narrow class distributions that low concave distributions. So that would be nice race there because I mean I kind of want to look there because it's we have distributions in several points. So there we can try to just kind of solve the relation problem and just find the right route.
There are many answers to that question. I think I don't know about log concave specifically, but the general philosophy, I think there are many answers to that. We actually have with other collaborators, like from the other part of the talk, we know that for symmetric distributions, if it's symmetric about the mean, then things are actually captured by more by Fisher information rates than variance kind of rates. So that's one answer to that. The second answer to that is that if we also have some unpublished result that says that ignoring constants for now, the constant hard problem is difficult to do. But one might ask, can we maybe have an estimator that achieves better than the sub-Gaussian rate for certain distributions? So for Gaussians, it gets this error, but for other distributions, it actually does better. Yeah, the answer is basically no, if we want the estimator to work for all distributions of finite variance. Basically, what you can do is take any distribution, you can construct a slightly skewed version of the distribution such that their means are separated by something that is almost sub-Gaussian, but they're indistinguishable. The caveat is that in finite samples, you can actually do a little bit better than sub-Gaussian rate, but in some asymptotic sense, you cannot. So that's what we'll be able to show. So general intuition is, if you have a distribution and then you hide an extremely tiny amount of mass all the way out there, that kind of increases the variance by a lot, but the mean isn't shifted by anything, then, your samples are going to be from the core distribution, but your error rate is going to be according to the variance of the core distribution, not the big variance. So in this finite sample sense, you can actually sometimes do a lot better. But asymptotically, as you get more, if you fix the distribution and take more and more samples, you will eventually see, that hidden mass out there. So then eventually you'll get back to the big variance rate. So finite samples, you can do a little bit better, but asymptotically, this is actually optimal, at least up to a big O sense. So yeah, I hope that was yeah. But yeah, it really depends on exactly which class of distributions we consider as well. As you pointed out, if we restrict them, maybe we can do something better. Cool. Ready to move on? Yep. Great. So next part of the talk is the second story, natural generalization to high-dimensional mean estimation. So here we could measure the error of the mean estimate by Euclidean norm in L2 norm. And as for assumptions, we also need to assume that the mean vector exists. And now we're going to assume that the entire covariance exists. So every direction, the variance is finite. Okay. According to our recipe, again, we now first want to look at the asymptotic theory. What are the guarantees we want to achieve? So to do that, we really need to analyze what is the tail of a high-dimensional Gaussian with covariance sigma over little n. Okay. So to see how this Gaussian behaves, well, first observation, high-dimensional mean estimation is, of course, at least as hard as one-dimensional mean estimation. So we can always look at the maximum variance direction, and we expect to do no better than this hopefully somewhat familiar expression by now, where we replace the variance by the operator norm of the covariance inside the square root.
Just a very good question. Like, like the bounds going to be in the one or in the
L2 norm, Euclidean norm. So everything is Euclidean norm. Yeah. In I guess Mahalanobis norm, I guess there will be similar questions to ask. I haven't thought too much about them yet, but yeah, L2 norm for now. Yeah, so there's a low dimensional phenomenon, one dimensional phenomenon. In the maximum variance direction, we expect this kind of error. But what about actual high dimensional phenomenon? Well, one of the most famous things about high dimensional Gaussians is that they concentrate actually like a shell instead of around the origin, something like this. And what's the radius of the shell? The radius of the shell for a high dimensional Gaussian is square root of this trace of sigma, so sum of variance directions divided by n. Okay, so these are two basically lower bounds of what kind of error we would expect. And as it turns out, if we just add these two terms together, we could actually show that the Gaussian is this tail. And therefore, up to this 1 plus little or 1 stack, we are going to aim for this. This is the high dimensional mean estimation problem, what we would aim for, if we want right constants. We haven't solved the whole problem yet. This is still wide open. Happy to talk about it if you have any ideas. It seems challenging. Paul and I have thought quite a bit about this, but let me just describe some of the prior works. Starting from Lugosi-Mendelssohn, they showed some exponential search kind of algorithm that achieves bigger optimal error for this kind of error rate in all regimes. Hopkins did a sum of squares relaxation that made the estimator polytime. And then there are other improvements that brought it all the way down to essentially near linear time. Yeah. Sorry, exists some constant such that this error rate holds. So instead of 1 plus 0, it might be
yeah.
Under minimal assumptions, yeah. In all these cases, yeah. So there's a long line of work people have looked at this. They do get bigger optimality, just not very good constants as far as I can tell.
I'm not sure what's this consequence.
Sure, yeah. Okay, yeah. So last line of work, I just want to briefly mention this line of work does near linear time bigger optimal rates, but also are robust in some optimal way to adversarial outliers as well, corruptions as well. So all these are bigger optimal. What we want to do is to get the right constant for the mean estimation problem. We haven't quite solved it, but I want to tell you about one recent work that specifies is in a very high dimensional regime that we do get the right constant for. So let me now concretely define what I mean by very high dimensions. We're going to measure according to the covariance matrix. So maybe let's start with the pictures here. For certain distributions, we might have a spherical covariance, so it kind of just looks like a sphere, high dimensional sphere. Intuitively, that has a high effective dimension. On the other hand, certain covariances might have very small variance directions. The covariance, the ellipsoid, actually looks more like a pancake. And intuitively, we want to say that this is an effectively lower dimensional object, even though it lives in d-dimensional space. And the concrete way we measure effective dimension, or I think in other fields, sometimes they call it effective rank, is by looking at the trace of the covariance, so sum of covariances divided by the maximum direction. So for something spherical, you get exactly d. For something with smaller covariance directions, you get something strictly smaller than d. Now, why is this quantity directly relevant to our problem? The observation is that if we look at the error we were aiming for, if the effective dimension is much bigger than log 1 over the failure probability, then the error is actually dominated by just the first term. It's within a 1 plus little 1 factor of just the first term. And our result is almost matching this observation. We relax this a little bit. If the effective dimension is much bigger than log squared of 1 over delta, then we get the right error rate with the right constant in linear time algorithm as well. I just want to maybe briefly say that in practice, this is actually a relevant regime because like delta, no one's really going to take it smaller than 10 to the minus 30, like some age of the universe kind of thing, And log squared 1 over delta isn't that big, whereas we do have really high dimensional data, like tens of thousands of dimensions, if not millions of dimensions. So this inequality is not that hard to satisfy. So this is actually a relevant result that we've got in practice. Now I'm going to show you an even simpler algorithm that's even easier to implement. In fact, it could be an in-class demo. So even simpler algorithm. So again, we take n samples, failure probability. Now we are also going to compute a yeah.
So the previous slide.
Yeah.
The term, on the left hand is the top. On the right. Okay. So on the left, what happens is that when ZF is bigger than the log 1 over delta, then the second term is dominating failure.
Yep.
And this is kind of the right way when it is dominating. What happens on the right? Is it the same story, but the tail is with the log square?
Yeah. So our result applies when the assumption that the effective dimension is much bigger than log square. Yeah.
The result themselves, then the part of including the log square of 1 over delta, how does it? What is this part?
Are you asking what does a little or 1 look like, or what?
Basically, what in your results, what would happen instead of the square root of 2 with the rate of 1 to do with that?
Like you're asking how the delta shows up in the result.
Yes, yes.
I
I
see.
mean, and I understand that, I'm not foreign to this thing, so I understand usually we try to do, if Z is bigger than log.
Yeah.
Then the rate holds.
Yeah.
The rate itself is this, and then you want to kind of do the two things to be consistent. So, that the rate should become valid as soon as, the second term is completed.
Right. So we don't have that. We have a slight gap in the regime. Yeah. Maybe another way to phrase this is that if for every delta that is not too small, so if delta is too small, this inequality is violated. But if delta is never too small, then you can, it's not the algorithm I'm going to show you, but you can rephrase the algorithm such that it for any delta value up to some e to the minus square root of effective dimension, then for any of these delta values, the same estimator is going to get this guarantee with that failure probability delta. Does that make the quantification a little bit clearer?
I think so. We can discuss it fine.
Yeah.
The most important thing is that the answer is there. So.
Yeah. It's basically what we have is actually a multiple delta estimator in the De Broglie et al. Sense.
It's just like adaptation.
No, because it's kind of all we really need is to know that the effective dimension is big. So then we can just use the effective dimension in place of wherever we would use a failure probability. So you can kind of just, yeah. So then it kind of just applies all the way down to that smallest failure probability, and then you just end there. So any smaller failure probability, we don't get the guarantee. Yeah. But yeah, that's a good technical question. Yeah, I was being a little bit heavy about this. Okay, even simpler algorithm. So we are going to compute some rough mean estimate again, but in high dimensions, there's no obvious good generalization to median means. So we're just going to do a coordinate wise. So for each dimension, we just do median means. And key point here is that this is no longer big or optimally accurate. In fact, this is quite bad as an estimate, but it doesn't matter, as it turns out, for our applications. And then again, we're going to refine it into a nice estimator. And this is an even simpler algorithm. Look at each sample and look at how far it is from the rough estimate and just remove the farthest one. So to answer your question a little bit earlier, like here, I'm choosing like roughly like log square 1 over delta many samples. It could also be a lower bound to the effective dimension. So then the algorithm could, in some sense, be like delta independent as well. So once we have that, just remove these points and compute the sample mean of what remains. Yeah. Sure. Yeah. E to the minus square root effective dimension. Then if it's for fixed delta. Yeah. So even simpler algorithm. This might even look a little bit too simple. So let me just at least hand-wavily justify why this could possibly work. One thing before that, one question you might have, I said that I've been asked before is, I just told you that we know how to do one-dimensional mean estimation, and there's this very high-dimensional mean estimator. Is there maybe some way to interpolate them to get something that works in all regimes? That's a very obvious question. Paul and I did think about it, but we don't know how to do it, and I think there's a good reason. The two estimators are actually doing something fundamentally different. And to see this, one obvious evidence is that in this high-dimensional estimator, we delete log square 1 over delta many samples in an unweighted manner. Whereas in the one-dimensional thing, we delete single log 1 over delta many samples in some weighted manner. So in that sense, it seems to be a gap that we don't know how to quite bridge between the two styles of estimation.
The log square is an artifact of, not artifact, but like there should be probably a way in the high-dimensional regime to make it global.
Yeah, I even believe that the full problem should be solvable as well. It's just that this particular algorithm, I don't think is the right. I have no reason to.
Evaporates if we solve the log square problem.
Sorry, can you repeat it?
Objection. It relies on saying that we delete log square. So if we were to do log, this would imply that now.
I haven't thought too much about it, but I think from what I recall from my discussions with Paul, I don't think we believe that this estimator could cover up to the log. It actually is a log square kind of thing. So we might need to change the algorithm to even cover, just the high dimensional regime, let alone the full thing. But this is a super simple algorithm and it works in a lot of regimes. That's why we, I think it's worth, telling people about it. So just very simply, this is the most hand-wavy slide in the entire talk. Why could this possibly work? And this is based on a famous fact by Telegram and Bousquet, which says that if you have bounded random vectors, if it's mean 0 and it's always bounded within radius r of the mean, bounded random vectors, if you take the sample mean of a bunch of samples, they're actually pretty well concentrated. In fact, concentrated exactly the right way that we would want them to. I'm being super hand-wavy about quantifications here, but that's just a high-level philosophical fact. The little one here, of course, depends on the bound r. The stronger the assumptions, so the smaller r is, the little one gets better and better as well. So why is this relevant for our algorithm? Here's a very simple rephrasing of the algorithm. So first we recenter according to some rough estimate, and then the second step was just truncating the farther samples. This is roughly equal to just saying that you look for some radius r such that everything outside of the radius you delete, right? So in that hand-wavy sense, you can apply this theorem, this fact, Bousquet inequality. Of course, it doesn't quite work this way because the radius r also depends on the samples, but this is stuff that is fixable with a bunch of triangle inequalities and union bounds, basically. So, fundamentally, this is what's happening. Bounded random vectors concentrate well. And yeah, so this is the second part of the talk. I showed you.
I saw recently in some talk that talk of the vast estimation. Unfortunately, there was this.
The very high dimensional thing, I don't see any reason why repeating would help. Just because the very high dimensional, like this, we already saw with some really rough estimate that already works. And I think even improving it to something much more accurate isn't really going to help because the two steps are so insensitive to the initial thing. So I don't think that this algorithm is going to help. For the one-dimensional thing with the same philosophy, I think it will help in practice. It's just that for analysis, we show that one step works. That's why we kind of presented it that way. But in the one-dimensional estimator, like I would even sometimes actually run it a few times or run it to convergence. It's a completely reasonable thing to do. I guess also any questions on Zoom, please feel free to ask. How are we doing on time, by the way? I have no idea. Oh, okay. It's okay if I don't finish everything as well. It's nice to have a discussion. Yeah, any questions?
I mean, just the previous question, the version was that have some optimization in the beginning, and I thought the further stages of optimization will improve.
Yeah. At least for the purposes of the analysis, but given our analysis of what's happening for the high dimensional estimator, it's not like a fixed point kind of thing. For the one-dimensional estimator, we do have a fixed point kind of analysis, whereas the high dimensional thing is not that. So which is why I'm saying that at least my understanding is that one-dimensional, I could see how fixed point, like running to fixed point would help. The high dimensional thing, I don't see it. Yeah. Just because of our analysis.
I can just tell you that it's famous when covariance estimation that this idea worked, it wasn't always defined the sum. It's just like I'm saying that the invariant which this
for the iteration.
Yeah,
I see.
Oh
yeah, sure. Yeah.
From experience, this might be
sure. Yeah. That makes sense. Yeah. Cool. So I guess I'll move on to the last part of the talk. There's a bit of a twist there. That's why I do want to tell the last part of the story. So location estimation is just switching gears a little bit. Here we know the exact shape, this shape of a distribution, and we get some unknown shift to version that we get i.i.d samples from. So like these stars here, some shifted version of the dotted line density. And the goal is to estimate the shift with high probability again. Now, back to the recipe, what is the asymptotic guarantees? This is pretty standard parametric statistics. What the theory recommends is to use the maximum likelihood estimator. So what you do is basically shift the density such that you induce the best possible likelihood of inducing these samples, and that is your MLE, maximum likelihood estimate. And the asymptotic theory says, again, it also enjoys a central limit like asymptotic normality like guarantee. If you fix the distribution and take the number of samples to infinity, the asymptotic Gaussian has variance controlled not by the variance of the distribution, but by something called the Fisher information of the distribution. That I'm going to define in a bit in case anyone is not familiar with the notion. The thing I want to wrap up the asymptotic theory that I want to mention is that there's a corresponding Kramer-Raulo bound that is super famous. That says that for every shift invariant estimator. So again, shift invariance means if you add 3 to all your samples, you should also add 3 to your output estimate. For shift invariant estimators, the variance must be at least 1 over n times the Fisher information as well. So that kind of matches the asymptotic theory and gives evidence that the asymptotic behavior is actually optimal. And also observe that the MLE is shift invariant for one thing, and therefore the bounds actually apply. The other point I wanted to mention is that the sample mean is also shift invariant. So the asymptotic behavior of the sample mean is at least as bad as the MLE. Yeah, that was the point I was going to make. So yeah, at least according to Wikipedia, it says it does. So okay, the Wikipedia version of Kramer-Raulo says it does. There's some term that depends on the derivative of the bias. So with shift invariant, the derivative is always 0. Yeah. So let me just define Fisher information for anyone who might not be super familiar with the notion. The Fisher information is defined by this integral, which is the derivative of the density squared divided by the density. It basically measures how jagged, how much ups and downs the density has. So on the right here, we have a big Fisher information kind of distribution because there's lots of ups and downs. And for Gaussians are very smooth. They have a small Fisher information. And just to be a little bit more concrete, to give examples, for Gaussians, the maximum likelihood sample mean is just a sample mean. If it's a variance sigma squared Gaussian, then the 1 over the Fisher information, which is the asymptotic variance of the MLE, that also has sigma squared kind of error rate. For a Laplace distribution, so a Laplace is like something that looks like this with the e to the minus cx kind of density. Yeah. So sample median. I usually give this talk in a CS setting, so I want to actually define this more properly. MLE is a sample median. If it's a variance sigma square variance distribution, then 1 over the Fisher information is actually winning by a factor of 2. So asymptotically, the sample median actually does better than the sample mean for Laplace. And this kind of wave distribution, we can MLE has no closed form, at least not as far as I would know. We can make the 1 over the Fisher information arbitrarily small just by shoving in a lot of waves, basically, just to get some intuition. Okay, so with that, let's get back to again the recipe I introduced at the beginning. What is the the next question was how do we actually make the MLE fail in finite samples? Why is it sensitive to certain behaviors in finite samples? Okay, it turns out it's actually not hard to fool or make the MLE fail in finite samples. So consider the distribution that is just a core standard Gaussian, and very far away we hide a tiny bit of mass that is much less than 1 over n. So with n samples, we expect to not see anything from a Dirac delta spike very far out. So let's say we get a bunch of samples here. Intuitively, we know that it's probably not from the Dirac delta spike. So what we want to do to get a good estimate is to shift it all the way such that the Gaussian matches the samples, and that gives a good estimate of the mean of the shift. But what the MLE does actually is to shift the Dirac delta spike all the way to the rightmost sample of what we observe. And the reason for that is that a Dirac delta spike has infinite density. So in this kind of degenerate sense, we can't win infinite density. We have to match the infinite density to one of the samples to get maximum likelihood. So this is a very simple way that the MLE fails. So we will need to correct for that in the algorithm that I'll tell you in a few minutes. Now, the goal, again, is to achieve error rates according to this kind of pretty familiar expression by now, hopefully, is that the variance, now we have 1 over I, 1 over the Fisher information inside the square root. That would be what we want to achieve.
Just also, now the setup, so it's again one-dimensional, but now what is the vertex plus, like the classic distributions?
Oh, this is now essentially any density.
Okay, so just in terms of the Fisher information.
Just in terms of what now we want to achieve a Fisher information kind of rate. Yeah. So just changing gears. So instead of variance rates, we want Fisher information kind of rates. And we want the right constant because that's what the asymptotic guarantees of the MLE is. Yeah. And again, the goal here is that we want a 1 for 0, 1 to be like distribution independent kind of convergence to the asymptotic Gaussian. The twist here is that it turns out that's actually impossible. That was a surprising fact to us when we worked on the project. And the counterexample is actually really simple as well. Look at a standard Gaussian, the standard Gaussian, and then in the central region, we just insert a sawtooth that is very, very fine of sawtooth with W. Take W to 0. So what happens is that you get very, very sharp edges. So you get a lot of derivatives. So you can essentially just pack Fisher information in there. But the density is, if you take appropriate limits, the density is just going to look like, just like the Gaussian. So at least in certain regimes, I'm going to make a little bit more precise in a bit. In certain regimes, you don't expect better than Gaussian kind of error behavior, even though the asymptotic theory says that we have close to infinite Fisher information, so we should get infinite accuracy. It's a bit of a degenerate example, but that's showing why the asymptotic theory isn't like capturing what's happening in final samples. So let me just make this a little bit more precise what this example is doing. On the right-hand side, we can actually show an information theoretic lower bound that applies to all algorithms. So this is not an issue for just the MLE. This is an information theoretic issue. X-axis is the number of samples, and y-axis is think like median estimation error for the lower bound, normalized by root n, just to get rid of the 1 over root n rate kind of thing. The intuition, so the point here is that there is actually some phase transition. The intuition is that so the sawtooth is giving us all this Fisher information, right? So when do we actually get to leverage the sawtooth? It is when we get to align the model to within one sawtooth. That's how we can actually use the sawtooth. If we don't get that, then the sawtooth is kind of useless. Okay, so when do we get to within one single sawtooth? For Gaussian, we need 1 over W squared samples in order to get to up to error W. So before that, we don't get to within one sawtooth. The error is just like the Gaussian case. So that's much larger error. And only after that, we could possibly get the asymptotic theory kind of predictions that we get much higher accuracy. And point. So take the right appropriate limits of, just take with W and maybe like the derivative, the slope might be like 1 over square root W or something like that. So the derivative is going to tend to infinity, but the density is going to tend to just like the Gaussian. Something along those lines. Also, I might have meant W square, but yeah. So we can make W like as small as possible. So this is showing that it's impossible to get distribution independent convergence to asymptotic theory guarantees just because of this strong like information theoretic lower bound. So now we still want some finite sample theory. We still want to apply the recipe, but now we need this theory that kind of respects this kind of phase transition kind of behavior. This is inherent in this particular distribution, for example. So we need something other than the Fisher information as a quantity to capture the right rates for finite sample behavior for location estimation. And he is a proposal. It's not the tightest thing, but he is something that works in many distributions. So let's consider taking the original distribution, and then we're going to blur it a little bit with a tiny Gaussian of radius r. And now let's look at what's the smooth Fisher information. What's the Fisher information after smoothing it? So this is a pretty much exactly the same plot. If we blur this sawtooth by a width much smaller than the sawtooth width, so much smaller than W, then the sawtooth still exists. So there's still like close to infinite Fisher information. So that's the first region here. And when we blur out the entire sawtooth, if the blurring radius is bigger than W, then the Fisher information kind of just goes away and it becomes just a Gaussian case. So the smooth Fisher information actually also exhibits the phase transition that we are looking for. And so we're going to write down a theory, at least an algorithmic upper bound, that says that we can achieve rates according to the smooth Fisher information as opposed to just the vanilla Fisher information. So that would be the goal. And that's exactly our result. Instead of getting Fisher information rate, we get something that is proportional to 1 over the square root of the smooth Fisher information. And the result here is that we have some explicit rate of R that I'm not writing down here, but that goes to 0 as you take the number of samples to infinity. So the amount of smoothing required does decay in the number of samples. So eventually we'll get back to the true Fisher information rate. And the little over 1 here, we can write it down explicitly in a distribution independent manner. So this result is really capturing all the distribution dependence in this kind of smoothing. So this is a new finite sample theory, and this is achieved by what we just call an R-smooth maximum likelihood kind of estimator. And the result is this is like no worse than like using a sub-Gaussian mean estimator, even my previous result. Like even just using this estimator, if you blur it and if you get the density information, you should actually use it. Like this actually gives better guarantees. And the algorithm is also pretty simple. As you would expect from the name, what we do is we compute a blurred version of the model, just blur the distribution. And then we take n samples of samples already from F. How do we get samples from a smooth version of F? We just add Gaussian noise to them. And once we have that, we can basically just run the MLE on the smooth model and the blurred samples. It turns out that that is enough to fix most of the issues. And the point is that, remember the Dirac delta spike example I showed you before. Once we blur it with the radius R Gaussian, then the density is no longer infinite. So that kind of, in a very simple way, fixes that annoying example. How are we doing on time? Maybe I'll just end it here. There's some technicalities. This is not quite the way we present the algorithm. We change it a little bit to make it generalizable to high dimensions, but it's not, maybe not super important. Yeah, so there's some other stuff that makes it a little bit simpler, but yep, okay. So just to recap, at the very beginning, I introduced a recipe for looking at estimation problems. We looked at what's the asymptotic theory guarantees, what's the algorithm we recommend, and then we looked at why does it fail? How does the simple algorithm fail? And then we asked, how can we fix the simple algorithm to get better guarantees, and in certain cases, optimal guarantees. I applied this recipe to 3 different problems, to one-dimensional estimation, and then to a very high-dimensional estimation problem. Turns out for these 2 problems, we can actually achieve asymptotic rates in finite samples with the right constants. But unfortunately, for location estimation, the answer is kind of, it turns out it's impossible. But we can still use the same philosophy to improve the underlying algorithm and get a result that is morally has the same flavor as the previous results. So yeah, that's pretty much the talk. And if you're interested, I'm happy to discuss really quite many interesting open questions, I think, along this line of work. So let me just end this here.